So if we're going to look at elements within chemical equations and chemical reactions, there's some elements that have to exist as a part of a pair. Okay? Some elements are not stable just to be hanging out as individual elements. They have to exist as a pair. Okay? These are called diatomics, okay, or diatomic molecules. Okay, di means two, so two atoms. That is a diatomic molecule. And we have a whole list, not a big list, but a list of these molecules that if they're to exist in elemental form, they exist as a pair. Okay, so on page 263, there is a table that has the list of diatomic molecules. Okay, I'm also just going to list them up here on the board if you don't want to take a look at that. But so our diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. What these diatomics mean is that if I say a reaction has taken place with oxygen and hydrogen, we can't just write H plus O equals water, or H2O, okay? These cannot exist in single elemental form, okay? They've got to exist as a pair. So it has to be H2 plus O2, and then we'd work to get our product there. Okay, does that make sense? If we're talking about an elemental version of hydrogen or oxygen or chlorine, fluorine, any of these diatomics, they've got to be in that pair. So it's H2, O2, N2, all that kind of stuff. Okay, any questions about diatomics? That's a list that you'll have to know, have to be familiar with, okay? All right, so these are some symbols that we're going to go over that are used in chemical equations quite often, okay? So if you see a S with parentheses around it, that means it's in solid form. An L is liquid form. A gas is just a G, okay? That means it's in gaseous form. If you see an AQ in a chemical reaction, that means it's an aqueous solution, which means it's been dissolved in water. If you see a single arrow, it means that's a chemical reaction taking place from the reactants to the products. Okay, so the arrow kind of means like yields or equals or however you want to say that. Typically it's said to be yields. Okay, A plus B yields C and D. Okay, and then our double arrow means we have a reversible reaction that can go back and forth. So this is just a kind of list of things that you need to be a little familiar with when you see a chemical formula given with a little G beside it. That means it's a gas. If you see it with an L, it's a liquid. An S is a solid. Okay. So here's just an example of what a chemical reaction would look like with these symbols plugged in, with some chemicals plugged in right here. Okay. So do you guys understand what a coefficient is in a math problem, right? If I have 2x, 2 is my coefficient. Okay, we're doing the same thing here. We're adding numbers as a way to represent more of something. Okay, a greater amount of something. Okay. So in order to satisfy our law of conservation of mass, we may need more than one hydrogen molecule or more than one oxygen molecule. And if we want to do that, if we need more than one hydrogen molecule, we can't just say H3 or H4 because that's changing the integrity of the entire substance. That's an entirely new substance. So if we want more hydrogen molecules or hydrogen atoms to balance our equation, we would add a whole number coefficient in front of that compound. Okay? Coefficients must be whole numbers. Okay, so let's say, just for the sake of practice, if I needed to have 8 hydrogen atoms on one side of my equation, what coefficient would I add to this compound right here? I would add 4, okay, because this is H2, so that's already 2 hydrogen atoms, and if I need 8 total, I add a 4 coefficient there. Okay, does that make sense? Okay. So if I have something listed as 2H2O, that means I have 2 separate water molecules there, okay? I have 4 total hydrogen atoms or molecules and 4 total oxygen atoms, okay? Technically that should probably say atoms instead of molecules, if we want to be 100% correct, okay? So technically I have 4 hydrogen atoms and 2 oxygen atoms. Okay? It allows us to balance the equation, and it allows us to see the relative number of moles of substances in this chemical reaction. Okay? If I have this reaction listed here below, okay, we don't have to know the names of these. These are hydrocarbons. We don't need to know, okay? This is C10H8, then I have 12O2, yields 10 CO2 and 4 H2O, okay? So if I'm looking at this chemical reaction, I know that 1 mole of this substance is reacting with 12 moles of oxygen, and it's yielding 10 moles of carbon dioxide and 4 moles of water, okay? So those coefficients also serve as a way for us to view relative number of moles, okay? Why do you think the number of moles doesn't necessarily have to add up on both sides? Because here we have 1 mole plus 12 gives us 13. This side has 10 plus 4, which gives us 14. Why do you think the number of moles of something doesn't have to add up? But the number of molecules does. Or number of atoms does. Yeah, Alex, what do you think?
I think each element's weight is different.
Yeah, that's exactly right. Each atom has a different mass, okay, or the different atoms represented in here have a different mass, which means the moles and mass ratio aren't necessarily exactly the same, okay? So the overall mass has to be the same for products and reactants. Moles won't necessarily always be the same, okay? So you don't have to worry about that as part of balancing your equation, okay? Okay, so let's walk through the steps for balancing equations. This is, I think, a fun part of chemistry, believe it or not. It's fun and easy, I think, because you have a specific right answer. There is only one right answer, and there's ways to check yourself, okay? So if we give you a formula or a reaction that takes place in word form, if I say magnesium chloride reacts with hydrogen to give us hydrochloric acid and magnesium, you need to be able to break those words down and write their chemical formula, okay? So if I say magnesium chloride reacts with hydrogen, I then write down magnesium chloride, which is, what's the chemical formula for magnesium chloride? Magnesium chloride, okay? So you've got to be able to translate those words into chemical formulas. If I say it reacts with hydrogen, okay, that means I mean elemental hydrogen, which is H2, okay, because hydrogen is one of our diatomics. If it yields hydrochloric acid, anyone know what the formula for hydrochloric acid is?
HCl.
Yeah, good. HCl and magnesium, okay? So there we took words, made them into chemical formulas, and wrote our own chemical equation. Okay? This is not balanced yet. We're gonna work our way there. Okay? It's not balanced, that's okay. But we're gonna get there. Okay? So you've got to be able to see the words and put them into chemical formulas. Okay? After that, we start balancing. We start our actual act of balancing. If our reaction is given to us with chemical formulas already, great, first step's already done, okay? When we start balancing, we balance each atom one at a time, okay? So we start with the nitrogens, and then we go to the carbons, and then we go to the oxygens, or whatever order you want to go in, okay? So these are guidelines we're going to go through. Go ahead and write them down. I want to get through all of them, and then we'll talk about them situation specific, okay? So we want to balance each atom one at a time. We typically begin with elements that only appear one time on each side, and I'll kind of show you what that means here in just a second, okay? We also have the opportunity to balance polyatomic ions that appear on both sides of the equation. So if you begin with sodium phosphate and you end up with phosphoric acid or something, phosphate is on both sides of the equation. You may be able to keep those whole instead of splitting them up by atoms, and we'll look at that when we talk about balancing here. Okay, most of the time you're going to balance by individual atoms, okay, chlorine, then carbon, then nitrogen, whatever the atoms are. More often than not, you're going to want to balance hydrogen and oxygen last. Okay, they're going to be the easiest to kind of fit into the last spot. Okay. More often than not, you're going to want to do those two last. Okay, balancing equations becomes sort of a puzzle. Okay, it might take you more than one try, so I would really suggest you, when we do balancing equations, to do them in pencil, because it's going to take you more than one try. Okay. However, there is only one correct answer, and you will absolutely for sure know that it is correct. Okay, if you do it in the right steps. Okay. You might have to try a lot of times, but it's going to be okay. Okay. Okay, so as I start to balance this equation, I'm going to list all of my elements here, and I'm going to say this is my reactant side, this is my product side. So how many chlorine atoms are in the reactants side, or on the left side of the equation? 2. Okay, and how many chlorines are on the right side of the equation? 1. Okay, so now we move to the hydrogens. How many hydrogens are on the left side of the equation? 2. And how many hydrogens are on the right side of the equation? 1, right here. HCl, just 1. Okay, so how should we go about balancing that? Any ideas?
Put a 2 in front of HCl.
Yeah. Yeah. What if we put a 2 right there? So then we recount. So I'll just change colors here so we can see it. We'll recount. So instead of having 1 chlorine on the right side, I now have 2. And instead of having 1 hydrogen, I now have 2. Which means this is balanced and this is balanced. Okay. So this is what it will look like. Okay, I now have 2 chlorines on my left, 2 hydrogens on my left. Now I have 2 hydrogens on the right and 2 chlorines on the right. So this was an easy one. Okay, did we see the process there? Okay, I think it's best if you list all of your atoms and balance by individual atoms. So I made a list. I counted the atoms on the left, counted them on the right, and just worked through this part of it until they were balanced. Okay, we're going to try a couple harder ones now. Okay. So before we start jumping in, I want you to remember just a couple key things, okay? You cannot add coefficients in the middle of a chemical formula. So if we would have had our last example, H2 plus Cl2 is HCl. Okay, you didn't see us try to put a coefficient or try to put a number here, right? We don't add numbers here because that changes the actual compound. Okay, that changes the entire thing. So you don't ever, ever, ever put coefficients in the middle of a chemical formula. Okay, once a formula is set in a chemical equation, we don't change it. We only add coefficients to it. Okay, so coefficients only can go in the front of a chemical equation, okay, or a chemical formula. So if we have HCl, that means the 2 needs to go in front, and it applies to the whole entire molecule. Okay. Questions about that? Don't alter the chemical formula. Okay, before we can really even get to that point, we've got to make sure that our chemical formulas are absolutely correct. Okay, if the problem asks for sulfate and you write sulfite, that's going to throw off your entire balancing process, right? Because if we're asked for sulfate, that's SO4, and you used sulfite, which is SO3, that's going to throw off your entire balancing process and you'll never get it because it won't work. Okay? We've got to make sure that all of our chemical formulas are correct for what was asked in the problem. Okay? Otherwise, it won't balance and it'll be a really, really long puzzle. Okay? Got to make sure those chemical formulas are correct. So maybe before we start balancing and if we start writing equations, you need to check those chemical formulas with me or with your partner first to make sure that you 100% agree that they are correct. Okay? We cannot change subscripts in a chemical formula. Okay, so just like in our HCl example, we didn't add H2Cl2. We don't add subscripts in a chemical formula. Once they're set, they're there for good. Okay. Okay, and our last little thing to remember is that we can reduce coefficients at the end if they all can reduce by the same number. If they are all divisible by 2, then we can reduce them by 2. So let's say if I have just our basic chemical equation up here, A plus B yields C plus D. Okay, so let's say I put my coefficients in here. I'll put them in a different color. If I have 2A and 4B yields 2C and 6D, are those all divisible by 2? Yeah, so I can reduce them so that it's just 1A, 2B, 1C, and 3D. Okay, I know that's a little sloppy for you to see, but we can reduce those down, okay? And if we have if we have a 1 coefficient in front of anything, that means we don't need the coefficient at all. Okay, so this would then read A plus 2B equals C plus 3D. Okay, we've got to reduce them if they're all divisible by the same number. So now if we have a 1, 2, 1, and a 3, can we reduce those down any at all? No, because coefficients have to be whole numbers. So we can't reduce them anymore. Okay? Let's try this equation. Copper plus silver nitrate yields copper nitrate and silver. Okay, so our first step here should be to list all of our atoms separately. So if we have copper, and we make our little lines here for each side, nitrogen, oxygen, and then we're done. Okay, so before I start manipulating anything, I go through and count how many there are of each element on each side of the equation. Okay. All right, so let's get the equation copied down, get your list made, and we'll start counting atoms, on each side. Okay. So how many copper atoms are on the left side or the reactant side of this equation? How many? 1. Okay, and you can go through and count coppers first and then silver, or you can count the whole left side of the equation, then the whole right. You can choose to do that however you want. I typically will go down this whole left column first, and then I'll go over to the whole right column. That's my choice. For some reason I did that, and now I just do it every time. Okay, so it's up to you if you want to count copper first, then silver, then whatever. That's up to you. Okay, so how many silver atoms do we have on the left side? Okay, how many nitrogen and oxygen? 3. Okay, so now let's jump to the right side of the equation. How many copper molecules do I have on the right side? 1. How many silver? Just 1. How many nitrogen? 2. Very good, because this 2 right here distributes inside. So we distribute that, so we have 2. How many oxygens do we have? 6. We distribute the 2 to the 3, we multiply, and we have 6. Okay, so where do you see somewhere that we need to make a change? out of this lineup? Can you see anywhere that we need to make a change? Put a 2 in front of the silver? On which side?
Left.
Okay, on the left side. So that compound is called what? Silver nitrate. So if we put a 2 here, so now this changes our table up top, right? So instead of having 1 silver, now we have 2. Instead of having 1 nitrogen, we have 2. And instead of having 3 oxygen, we now have 6. So now copper is balanced, nitrogen is balanced, and oxygen is balanced, but silver is not. How can we fix this 2? How can we make this a 1, a 2? 2 in front of what? Okay, so that would now make this a 2, which would mean that copper is balanced, silver is balanced, nitrogen is balanced, and oxygen is balanced. Okay? In the midst of these lists can get kind of messy. So even after you think you have it complete, I don't think it's a bad idea to just basically count through one more time. Okay? So let's say we're going to just make sure that we have a total complete count here. So on copper on the left, we have how many? We have 1. How many silver do we have on the left? 2. How many nitrogen? 2. And how many oxygen? 6, because we have 3 here. We have 2 of those whole molecules, which means we have 6. Okay? So copper on the right side. Nitrogen on the right side. Oh, I'm sorry. Silver on the right side. 2. And nitrogen. 2. And oxygen is 6. Okay, so now we have checked them all, and they are for sure balanced. All right? What questions do we have? Can we reduce it? Drew says no. Why?
Not divisible by pH.
Yeah. Yeah. If we have 1s here, we can't reduce those down because it would make a fraction, and these coefficients have to be in whole numbers. So if we ever have a 1 coefficient, it cannot be reduced. Okay? Good. So let's try these on your own. Do we need to do one more as a class, or you ready to go on your own? Let's do the top one together, and then we'll go on our own. Okay? So if you can't read it, it says aluminum plus bromine equals aluminum bromide. So we'll make our list. How many elements do we have here? We just have 2, right? So our list isn't very long. Shouldn't take us too long. All right, on the left side, how many aluminum molecules do we have? On the right side, how many aluminums do we have? These lines are just here for places for our coefficients to sit. Okay, they don't mean anything else. Those are just blanks for our coefficients. So how many aluminums are on the right side of the equation? Here's our arrow. We have 2 aluminums on the right side. Okay, how many bromines on the left? 2, because this is Br2. And bromines on the right side? 6. Okay, so not balanced, right? None of these match up. 1 and 2 and 2 and 6. So how do we go about balancing these aluminums? Yep, 2 on the left side for our aluminum here, which would make this 1 a 2. How about balancing this bromine? We make this 2 a 6. We need to put a 3 here, okay? And then if we can leave this blank, okay, we just change this, so now we have a 6 there. If we don't put a coefficient here, we just leave it, okay? We don't have to put the 1 there. Just leave it blank, okay? All right, let's try the next 3 on your own. All right, how do we balance the second one, potassium and bromine? Alex, what do you think?
I just put the 2 in front of the KBR.
2 in front of the KBR, and that was it?
Yeah.
Is that balanced? What are we missing?
And then the 2 in front of the K.
There we go.
2, 1.
That's right. 2, 1, 2, okay? Because we needed 2 potassiums here, which we can easily manipulate over here with our just potassium reactant. Okay, what about our second one? Makara, what do you think? Okay, the second one we're going to try. The sodium and the water.
Put a 2 from the Na on the left side.
Mm-hmm.
And then put a 2 from, wait, no, yeah.
Okay.
And then put a 2 from the NaOH. And then nothing from the H2.
Good. That's what I had. Are we in agreement there?
Yep.
Is that what everyone had? That's what I had. Okay. Do we need to walk through why that is? Are we good? Okay, so try this one on your own. Take zinc and hydrochloric acid. It tells you what it produces, which is zinc chloride and hydrogen gas, which is H2. Okay, hydrogen gas is elemental hydrogen, which is a diatomic. Right? We know that's going to be H2. We want to write a balanced chemical equation for this reaction. Okay, so take them from word form, build the chemical formulas, then balance the reaction. Okay, we've got to be careful about our chemical formulas. So zinc reacts with hydrochloric acid to form zinc chloride plus H2, or hydrogen gas. Is this a balanced reaction? Just writing it like this, is it balanced? No. What do we need to do to balance it? Okay, is that it? Is that what everybody had? Good. I agree.